You might be asking yourself, well, what if we had a negative number to start with? We shouldn't be subtracting numbers from it because that'll make it further away from being a small positive integer. So instead of subtracting multiples of our modulus, we can add them. Consider this example, 5.7.3. We have negative 278 and we want to reduce it mod 11. We want to get it to somewhere between 0 and 10. Well, negative 278 is negative, so we have to add something to it to get it to be a positive number. Now the 300 here, I know that that's not a multiple of 11. This is just a convenient number to add to this negative number so that we end up with a positive number that we can apply similar techniques as we did in the previous example. Once we get that 52, 44 is a convenient multiple of 11 we can take away from 52 to get that negative 278 is congruent to 8 mod 11. So now try this with a negative integer. Again, you're trying to do this by just kind of playing around with multiples. And notice there's a convenient reminder. We've said it multiple times already, but it's worth saying again. In modular arithmetic, the final answer is always between 0 and n-1 inclusive. So try this hands-on exercise, pause the video, come back. Now look at this more complicated expression. We have something squared multiplied by some number minus the product of two other numbers, and we're trying to reduce that modulo 7. The nice thing about modular arithmetic is that we can reduce each of these numbers separately and then make all the numbers smaller so that we're working with smaller, easier numbers. For example, we can take this 37 and reduce that mod 7, which gives us 2. We can reduce the 41 mod 7, which gives us negative 1. It's not a bad thing if we get a negative. It's a nice small number, negative 1, so it's not bad to have that. And then reducing the 53 mod 7, we get a 4. So we have 2, negative 1, and 4. These are much easier to work with than 37, 41, and 53. What does this tell us? 37 squared times 41 minus 53 times 2 is congruent to 2 squared times negative 1 minus 4 times 2. The 2 doesn't change, it's the same. It's already a nice, small, convenient number. When we simplify this, we get negative 4 minus 8, that's negative 12 mod 7. How do we bring this up into the range that it needs to be? Well, we just add a convenient multiple of 7 in this case. If I add 14 to negative 12, I get 2, which is in the appropriate range. Now, pause the video, try this hands-on exercise. Notice we have a different modulus, which is 9. So you'll want to apply the same technique to these numbers here. There's some pretty cool, interesting things you can prove using modular arithmetic, using this a notion of a congruence. You can prove some more general facts in easier ways. Here's an example. Show that if an integer n is not divisible by 3, then n squared minus 1 is always divisible by 3. Now you might have proved something similar to this in the past, and the way you had to do it was you had to write n as 3q plus 1 and 3q plus 2, because those are the two possibilities when n is not divisible by 3, And then you had to manipulate these complicated algebraic expressions. When we use the language of modular arithmetic, it makes things a little bit easier. So notice that n squared minus 1 divisible by 3 is the same as saying n squared minus 1 is congruent to 0 mod 3. Okay, so we're going to try to prove this using the language of modular arithmetic. All right. First way of trying to prove this, n is an integer not divisible by 3. That's what we're assuming. The only two possibilities then are that n is congruent to 1 mod 3 or n is congruent to 2 mod 3. So we have two cases, just like we've done in similar proofs previously, but we're not going to have to manipulate any weird algebraic expressions because we have this new language that cleans things up. Case 1, if n is congruent to 1 mod 3, then n squared minus 1 is 1 squared minus 1. Notice n is congruent to 1 mod 3, so I can replace the n with a 1. And so we get n squared minus 1 is congruent to 1 squared minus 1, which is just 0 mod 3. And that's showing, again, that n squared minus 1 is divisible by 3 in this case. Case 2, n is congruent to 2 mod 3. Well, now replace the n with a 2. 2 squared minus 1 gives us 3. 3 is congruent to 0 mod 3. In other words, n squared minus 1 is divisible by 3. Because remember, being congruent to 0 mod something means you're divisible by that something. There's an alternate way to think about this same problem. What if we have an integer n that's not divisible by 3? Again, that either means n is congruent to 1 mod 3 or n is congruent to 2 mod 3. Notice that n congruent to 2 mod 3 is equivalent to saying n is congruent to negative 1 mod 3. Negative 1, yes, it's negative, but it's a nice, friendly number to work with, a pretty helpful number a lot of the time. So that's, if I combine these two, or I should say these two congruences, that's like saying n is congruent to plus or minus 1 mod 3. Which means we have n squared minus 1 is congruent to plus or minus 1 squared minus 1, which is still going to be 1 minus 1, which is 0 mod 3. So we kind of combine the two cases into one calculation because we notice that in either case, because we're going to square n, the negative sign is going to go away. Here's a couple of hands-on exercises for you to consider and give a try to. So use modular arithmetic. Use the methods similar to the example we just went over to show that 5 divides n to the 5th power minus n for any integer n. And then, once you've done that, use modular arithmetic to show that n times n plus 1 times 2n plus 1 is divisible by 6 for any integer n. You might find it interesting to make a connection with hands-on exercises from chapter 3. So in chapter 3 we did some work with integers, and now we're formalizing it even more. We're creating a new number system. We're kind of solidifying that knowledge.